And now we are going to hear from Emily about the talk they have given at ICTC about building a nice data set for AI, which I think is an important feature to have in many of the data sources we deal with. Emily, the floor is yours.
Thanks, Adrian. Okay, well, hi everyone. As Adrian said, I'm going to be talking about designing effective training data sets for custom AI models. My name is Emily Dorne, and I'm a principal data scientist at Driven Data. Just a quick introduction. Driven Data is a data science and machine learning consultancy in the social impact space. This means that we work with nonprofits, research groups, governments, and really help them leverage the tools of data science and AI to do their work more effectively. We work across a lot of different subject matter domains, but we've been working in the conservation space for the last 8 years. We've run a number of online machine learning competitions in this space, doing species classification, depth estimation, individual re-ID. We've carried some of that work forward into open source packages to make it easy to run these models and code. And then we've also built tools like Zomba Cloud, which is what we're probably most known for in this space. So Zomba Cloud is a cloud application that lets you train and run machine learning models without writing any code. It's focused on species classification and works for both videos and images. So a couple of distinguishing features for Zomba Cloud. We have native video support. We actually got our start working with animal behaviorists who are exclusively working with videos. And then we also feature custom model training, again, without the need to actually write any code yourself. So why do we need custom model training? Largely due to just the really wide variety and diversity in camera trap data. As we all know, camera traps are used all over the place. We study different habitats, from jungles to savannas to underwater. We study different things, from mammals to insects to even weather patterns. And even when we're looking at the same thing, we might be using different levels of granularity, different taxonomic ranks. So what is to one person an antelope is to another person a red forest duiker. And so it's really hard to have just a single or even small set of pre-trained models to really capture the diversity that we see in conservation workflows. So the goal of custom model training is really to support conservationists in having models that are specifically designed for their use case. On Zomba Cloud, this is just a couple of screenshots to give you a sense of what this looks like. You upload images and labels, you click a button to kick off model training in the cloud, you go about your day, get some coffee, we'll send you an email when your model is done and ready for use in Zomba Cloud. So on the one hand, you might say, okay, so we have custom model training solved. Why have this talk? And the reason why I wanted to talk about the kind of more upstream step, which is what is the data that you actually put in when you're training a custom model? Because what is in your training data set really has a big impact on the ultimate performance of your model. So this is really the basic premise behind why I wanted to give this talk at ICTC. This notion that we know that custom species classification models are really important. We have tools that enable conservationists to train these custom models without needing programming experience. But what's in your training data has a really big downstream impact on the utility of your model. And so I wanted to kind of approach this talk really addressing some of the FAQs that we get from Zomba Cloud around how much data do I need? How many different label classes can I have? Should my label classes be balanced, or should I use the empirical distribution of what I've kind of observed in my deployment? So I wanted to give some strategies for creating effective training data sets to really help set practitioners up for success. So I want to talk briefly about kind of 5 strategies for training data set creation. Again, the basic premise here is that we have a full data set. This is what's come in. We've had our camera traps out, we've collected all of our SD cards, and now we're saying of that full data set, which images or videos are we selecting into our training data? So the first strategy here is including all the labels that you'll need. So your model is only going to learn the labels that you provide it. If your model has never seen a giraffe in training, it's not going to know it if you show it a giraffe in the future. So when we talk about including the label classes, we're talking about what are basically the outputs that you want your model to predict. Recommend aiming for, 20 or under total classes is a good ballpark to start. This is largely just because the more output classes you have, the harder the problem is for the model, generally speaking. Your labels are also going to depend on your use case. And so, as I was saying before, one person might want to group all the antelopes together, another might want to differentiate between blue duikers and red forest duikers. And so you want to think about your data, what is the level of granularity that you need, and then use that to determine what are those output classes that you want, and then making sure that you have examples for each of those in your training data. The second strategy is probably the most important one. It's really important to make your training data set representative. And what we mean by this is that your training data should capture the variation in your overall data. So if your training data doesn't represent that real world variation, your model is not going to do as well. It might fail or just underperform on new or underrepresented scenarios. So I want to just give you a couple of visuals when we talk about like what does representation mean? How do we think about this? And I'm going to do it with kind of not images or videos right now. We're just going to do it with shapes and colors. So here's an example where, here's our full data set. We've got circles and triangles. And then on the right-hand side, we've got this training data. And now we have this question of, is our training data here representative? So we'd look at what is the key dimension on which this data set varies, and that's shape. And so we've got circles and triangles, and we've got those represented both in the training data. So we'd say, yes, the training data includes all the shapes from the full data set. If our shapes here actually represent species, we've got cats and dogs, we can feel good that our model is going to learn both cats and dogs. It's going to learn both species. But oftentimes we have, more than one source of variation. So here I've added another dimension, shape and border width. And if we look at this in our training data and we say, is our training data representative of our full data set? The answer is no, because we don't have any examples of that thicker border width. And so here, we might pretend that border width actually means day and nighttime videos. So here in our training data, we only have daytime videos. We haven't shown the model any nighttime videos. So our model is going to underperform on those nighttime videos, right? We haven't captured both sources of variation in our training data. And lastly, to make it a little bit more complex, here's an example where we've got, again, two dimensions, two sources of variation, shape and color. And if we look at our training data and we say, okay, we've got both yellow and blue, and we've got both circles and triangles, aren't we good to go? And the answer here is actually no, because we haven't captured any of the joint variation. So all of our circles are yellow and all of our triangles are blue. And so imagine that instead of yellow and blue, this is actually summer and winter. And so now we've got cats only in summer and dogs only in winter. What's going to happen is that the model, if it sees something in winter, it's going to say, oh, that's a dog, because it has never learned that actually both cats and dogs can be present in that season. And so what the model learns is that species and season are now tightly linked rather than independent features. And so when you're thinking about how to make your data set representative, you're looking not only at kind of those overall sources of variation, but also that joint variation where possible. So this might sound like a lot or hard to do. And so the way to think about this is basically identify some of the key sources of variation in your data set. And then you can either intentionally sample within those through a tool like stratified sampling, or you can randomly sample your data and then plot distributions and do some of these visual checks, like I'm showing you on the right-hand side, where we're looking at, the counts of videos in the different splits across the different seasons. So common sources of variation that you might want to think about are things like location. Maybe you have different countries, national parks, transects represented in your data set. You might have different time of day. What are these things that you know from the metadata that you can do some of these checks on to say, yes, I've included daytime and nighttime videos. I've included, videos from different times in the year. I've included videos with different backgrounds, so different habitats, different vegetations, different camera angles. And that's really going to help your training data set be representative. The third strategy here is that more data is generally better. Computer vision models learn by seeing lots of examples and learning patterns, and so you want to give your model lots of examples to learn from. There's no magic number here. A reasonable default is at least 100 examples per class. This is a graph here where we were basically training uh, the same model, but with uh, increasing data set sizes. So here we took 5 examples per species and plotted the accuracy on a holdout set. And then we took 10 examples per species and plotted the accuracy on the holdout set, 20, 100, and 500. And you start to see that accuracy kind of getting diminishing returns post 100 examples. So this is just a good kind of starting heuristic. Again, more data is generally better, but this is a good starting point. I will say that harder problems do require more data. So common challenges that increase the difficulty for correct classification are things like small size animals like rodents, high occlusion or camouflage, nocturnal, low contrast. Even if you have a really large number of label classes in your data set, as I said before, that's a harder problem. Or if you have really high similarity between label classes that you are trying to differentiate, again, more data is going to be helpful there. So this is going to be context specific. Obviously, if you are a lucky duck that has data that looks like this and you've got clear, high contrast, large animals, you're going to need less data. I imagine that this probably isn't you. Mostly, I just wanted to show you some cool images here. We all know that our data looks a lot more like this. All right. Fourth strategy, give your model diverse examples to learn from. You want to include different views of the animal in different locations, time of day, time of year, camera angle, lighting conditions. It's really this diversity of views that helps a model learn to generalize. So if you have 10 captures of the same animal that look really different, this is a lot more helpful to your model than having, say, 100 captures from bursts where those images look super, super similar. So on the right-hand side, I'm showing you different variation, right? We've got different views of the animal. We've got some nighttime ones. We've got the animal in different parts of the screen. This is the sort of kind of diversity that you want to include even within a given label class. One note on data quality here, if you can't tell what an animal is, don't expect the model to be able to either. So you want to include both easy and hard cases, but avoid impossible cases like totally washed out images, things that are totally dark, corrupted images, etc. The last strategy here is try and then iterate. It's really important to evaluate your trained model on a holdout set and then use that information to iterate on your training data set. There is no single strategy that will always result in the most accurate model. If there were, I probably wouldn't be giving you this talk. We just have the list of things to do. So as models are trained, as I was saying, you want to evaluate them on data that was not used in training. You want your holdout set to include, again, those key sources of variation, so it should give you a representative idea of real-world performance. Common proportions for splitting up your full data set, you take 60% for train, 20% for validation, and 20% for that holdout set. The goal of looking at the holdout set and evaluating the model on that is really to see where is your model performing well and where is it performing poorly. There are lots of different metrics that are worth looking at here. I'm not going to go into those in detail today, but the idea being that like species or label class level metrics are helpful to say where are places where my model is doing well and where is it doing poorly. So in this example, like I might look at, domestic cats and say, okay, well, we're only capturing 8% of cats that are present in the data. But when we think it's a cat, we're right 100% of the time. And so this is a place where we probably need to include more data so that our model can get better at actually finding those cats because there are so many cats that we're not seeing. That said, there are trade-offs in adding more data. So if you improve one class in isolation, this can degrade performance on other classes if your data set becomes heavily imbalanced. So if you say, I want my model to get better at giraffes, and you add 1,000 photos of giraffes, your model's performance is probably going to drop significantly as it's going to overfit to those giraffes and forget those prior distinctions. So that said, a uniform distribution is a reasonable place to start, and then basically see the type of errors that the model is making. You can add more data for worse performing classes and then basically evaluate whether accuracy for that one species is trading off against another. So where does this leave us? In short, there's no single recipe that is going to work in every case. That said, there are some same defaults. You want to give your model enough data to learn from, start with around 100 examples per label class. Diverse data, again, matters more than total count. You want to prioritize that representativeness in your training data. So try to identify 3 to 5 main sources of real world variation and check that those are well represented in your splits. And then if at first you don't succeed, try again, evaluate the model on the whole dot set, use the cases where it does poorly to inform iterations on the training data set. And lastly, I just wanted to conclude with a couple of reflections from ICTC. This talk was really well attended, and I think that that spoke to just the value of custom models. There is strong sentiment that off-the-shelf species classification models just aren't sufficient for the diversity of camera trap data. And so I think that this talk resonated with folks because they're trying to figure out how do I actually create the models that are going to work for my use cases. There was also a lot of excitement in using custom models in new environments where the data looks very different, so underwater, insects. And so I think it might be interesting to think about some pre-trained base models in those environments because that's going to accelerate the custom models and allow people to provide less data than if they're trying to fine-tune a land model for underwater, for example. And lastly, I think that one of the other sentiments we heard is that it can be hard for practitioners to know what models exist and what models are worth trying as a starting point before they decide to train a custom model. There's a lot of models and tools in this space, and so a model inventory that can document and allow people to find what models to try out and where they can run them may be very helpful. So with that, I will conclude. Thank you all so much. And if you want to try out Zomba Cloud today, you can go to zombacloud.com.
Fantastic. Thank you so much, Emily. I really find this talk didactic, and we understand why it was so well attended as ICTC, because as you mentioned, there is a need for adaptation to the context. Are there any question in the chat? I'm sure they are. At least I have thousands. Yeah, they are. Prabhu is asking about the origin of data to train the model, wondering if we can extract data from open source portals such as GBIF, iNaturalist, or the Indian Biodiversity Portal. Emily, what would you answer to Prabhu?
The idea being, can we use data that's already on
data that is open to train this model?
Yeah, absolutely. I think the main thing is you want the data that you're training on to look similar to data that you're going to be using for inference. So if you're training on data that looks totally different, that's not going to help you with your downstream cases. But if there's data that exists that is on similar species or habitats, and you're using that to augment the data that you've collected, absolutely, that's data that can be used, assuming that licensing and all of those permissions are set up to do so.
Indeed, yeah, the permission are important. I think I would take the opposite, not the opposite, but a complementary answer on when you train a data set or you made a data set full of label that is specific, don't hesitate to share it widely. It's important for the community to have the specificity you have so we can like train bigger problem or on bigger problem for bigger areas. So don't hesitate to share your data and easier openly on these portals. There is another question from Joshua. Yeah, I think we have 1 minute left. Joshua is asking, where do you draw the line on the number of variation to include? For example, rain and time of the day will change the color and visibility. How much can be done in pre-processing or augmenting data?
Yeah, so part of this is kind of trial and error of seeing, I was recommending starting with like 3 to 5 of the main sources of variation. So like daytime and nighttime look really different. So that's a really important one. I think different like backgrounds again is a big one. And then it's looking at the sorts of errors that your model is making. And so if you're saying, hey, we're doing really badly anytime it's raining, that's a really good indicator that we want to make sure that we're capturing weather variation where we can. I tend to try to start with the sources of variation that you can identify from just the metadata alone, because it's otherwise you have to go through the whole process of labeling to then be able to say, here's the weather that's happening in each of those examples. So start with kind of what you can get automatically and then use that review process to then inform that next iteration.
Great. Thank you so much, Emily. And thank you to all our speakers today. I think it was a super good reflection of some of the very well-attended talks at ICTC. We hope to reconvene other variety hours where we highlight what happened there. This is the end of today's variety hour, but it's not the end of the call. You are welcome to stay for what we call the real happy hour, where you will have less of a formal chat. It won't be recorded, and you can ask your question directly to the speaker or take the time to interact on any other topic that they are burning to you. So thank you all for attending today, and let's move on to the happy hour. Bye-bye.